All right. Welcome to this new episode of Neural Information Retrieval Talks. My name is Sergi Castella. I work at ZF as a content creator. Yeah, I have with me my usual co-host,
Andrew Yates. I'm an assistant professor at University of Amsterdam.
Like I said last time, we have a forum for you to give us feedback and to just share what you'd like us to talk about next and all of this stuff. So please use that. It's in the description. That said, let's just jump right into it. Today we're bringing you this paper titled Evaluating Extrapolation Performance of Dense Retrieval by BEIR, Zhan and colleagues from a bunch of institutions actually. Beijing National Research Center for Information Science and Technology at the Xiaohui University and a couple other institutions from China. That said, before we get into the gist of the paper and we start diving a bit more into that, I'd like to reflect a bit on the broader topic of evaluation information in information retrieval. That's actually the first topic that we covered in this podcast, which I think is super fascinating, and we decided that we wanted to go back to that. So before offline, you were talking to me about how you think that's one of the kind of topics that you're currently most interested about in information retrieval, like the whole benchmarking and evaluation. Could you speak a little bit to that, why you think it's interesting, why you're excited about that?
Yeah, so I think I'm particularly interested in or excited about evaluation right now just because of how good neural models have become, right? It's hard to tell what is the right direction for making them better. And so we have to think about how we evaluate them. And just in IR in general, evaluation is a hard task, I think, because the nature of IR, we don't necessarily know what we're looking for. There's no fixed classes that you need to be good at. A system should be good at any query that it gets, not, these 100 sentiments that exist or animals, whatever. It's not really a classification task. So I think this makes it hard and it makes it really challenging because even as people's behavior changes, probably what exactly we evaluate change. So for example, 20 years ago, I think people were always issuing keyword queries. Today, we want to think about like natural language questions and natural language queries when we evaluate. So even if your information need is the same, like over time, what that information need looks like can change, the sort of documents can change. So it's sort of something that always needs to be paid attention to, I think, due to this zero-shot property where we just have to handle anything.
Yeah, no, I mean, I guess I remember when we were talking, like the first time we talked about this whole MS Marco and benchmarking, and I got introduced to some of these concepts. I felt like very often you run into these sort of very basic issues of sort of subjectiveness of what is relevant. And like, it seems like in the whole field of information retrieval is kind of filled with all of these kind of very hard questions to answer that depend on so many factors. It's not like a classification on an image of like whether something is a cat or not. Yeah. It's more like what is relevant to a hypothetical user. And like you said, like user modeling, behavior changes, there's so much to it. That said, in the current landscape of benchmarking information retrieval, what do you think is the biggest shortcoming or something that, in your opinion,
I think it's just really hard to scale everything up. So like the TREC style of benchmarking works really well where, teams participate, they submit some runs consisting of documents for each query. These are pooled and judged so you have some judgments. But it's hard to do this so that you have enough training data for a neural method. And so this is where things like MS Marco come in that are based on these shallow annotations. So for each query, you know that a document is relevant rather than knowing that a set of documents is relevant and a set is non-relevant. You only know that one is relevant. So, I mean, this creates difficulties in that the strategy works for creating enough training data, but it's much harder to understand, I think, what's in the data set. And you kind of see some of that with this paper where they find that queries in, for example, the development data set, or which they use as test, are similar to ones they trained on. And so it becomes harder to understand exactly what is in your data when you have enough data to train one of these models.
Yeah, no, that makes sense. So I have here, before we go into the paper, could you give us a bit of a kind of overview of the last, I would say 20 years or something like that, what have been important milestones of like data sets or benchmarks that kind of have defined the landscape in the next year? I mean, you've already hinted a little bit at that with the MS Markov, for instance, or TREC.
Yeah.
So how has that evolved in the field?
So TREC has been around for a long time. It continues to be around and to be useful, just maybe not as much for training data as evaluation data. For most of the past 20 years, I think TREC data has been the main thing to use both for training and evaluation, right? Maybe you train or tune some simple parameters on, the previous year's data, and then on TREC this year, you use that model to submit. But now with the neural methods, we need more data, so this is where MS Markov comes in, and this is one of I would say, the first big milestone. So I believe this was released in its original form in 2016. I don't remember exactly when this became the ranking data set we know today, within a year or so. Mm-hmm. But this was a big milestone because this provided just a huge number of queries and documents with relevance judgments for them in the shallow way, which gives you enough to train a neural model. Mm-hmm. And then really one thing I'll add is that then TREC performs some judgments on this MS Markov data so that we have dense judgments for some MS Markov queries. So starting in 2019, there were 45 or so, roughly, MS Markov test queries judged deeply by TREC. So this, I don't know if it's a milestone by itself, but it's quite important to have along with MS Markov, because now we have the sparse training data and some evaluation data that maybe we can have a bit more confidence in, which often does correlate with the MS Markov data we've seen. And then the other milestone I would mention was this maybe BEIR benchmark. Mm-hmm. There are, I think, advantages and disadvantages of it, but it's really nice to have a benchmark focused on generalization and I think cross-domain performance, because this is something, like I was saying, that we expect from IR, but it's not really evaluated if you train and test on the same data set with very similar queries, which is kind of what this paper gets to. Yeah,
absolutely. I mean, this whole topic of like transferring domain relates very strongly to the idea of extrapolation, information retrieval, and I do think like in even broader terms in machine learning, there's a lot of interest in, like, I guess it's kind of the gist of it is known that, like as long as you train and test within the same domain or like within the same data distribution or something like that, these models like you can perform really well. But how do you generalize and like these ideas?
Yeah.
All right, cool. Then let's just jump into this paper. So evaluating extrapolation performance of dense retrieval. So what do the authors do in this work?
Well, the authors make the observation that a lot of queries inside MS Markov are similar in different ways. So, for example, you could have a lot of queries about the same entity. Where was Bill Gates born? What is Bill Gates' net worth? So the information needed is different. Bill Gates is in both. Mm-hmm. Or you can have queries that are actually really close to each other, but maybe phrased differently. So, like one example they give, average wedding dress alteration cost. So this is kind of keyword flavor. And then another query, average cost for wedding dress alterations. So the terminology has not really even changed. Mm-hmm. It's just written more like natural language.
Yeah.
So they make the observation that these exist, and then they want to understand how this affects results on this data set. So like, are methods becoming better at interpolating, meaning are they better at variations of queries they've seen during training? So like, if you take what is Bill Gates' net worth and you replace Bill Gates with another celebrity, is this enough? So this is not so interesting because it's just, a minor change from what is maybe seen before. Or extrapolation, like a totally new query. So maybe an entity you've never seen before, and maybe even asking about some aspect of the person you haven't seen before. Where was their yacht built? Something like that.
Yeah, so actually you've already hinted at that, but throughout the whole work, like one of the basic terminology that is used is this interpolation versus extrapolation thing, which is kind of interesting because I feel like it's become almost a loaded term in many corners of machine learning. So, I mean, I think intuitively we can have a good understanding of what those words mean or should mean, but can you sort of give what we're going to mean from now on when we say interpolation and extrapolation in this context of information retrieval?
Yeah, and I think this is really the only easy way to define it, like intuitively in our context. So like interpolation, it would be taking queries that you've seen during training and being able to handle some query that's a small variation on that. So like maybe only the entity is changed, but what you're asking about the entity is the same. So assuming you can replace Bill Gates with another entity, you should be fine. Extrapolation means different from what was in the training. So this isn't really precisely defined. But, intuitively, if you have a question about biology, what does ATP do in a cell? If this was never seen in the training data, nothing about ATP or cells, this is clearly extrapolation.
Yeah.
It's very different. You could start to argue this is almost changing domains, and this is all very fuzzy, like where you draw the line between them. So intuitively, I think we can understand it.
Yeah, no, and as you see, this differentiation, even though it's a little bit fuzzy, and then it does make a difference, and there's interesting results to come from that. As a short plugin, I would like to highlight this. Last year, this discussion always pops up in Twitter and this stuff like that, like the symbolist and the connectionist and all these discussions. There was this paper from Yiqun and colleagues, which is from this mathematical perspective on interpolation and extrapolation, which kind of makes the case that interpolation and extrapolation, the intuitive understanding we have of those terms really doesn't translate well once you go to high dimensionality and like things start to break down. So that so basically we should be careful with how you use those things, especially when you're having abstract or like more kind of formal. More kind of in the abstract of intelligence and these kind of things. And I would recommend you check it out, because it was kind of really interesting to have that intuition bent. But it's not really relevant.
It's an interesting paper. Here I think the sense of interpolation extrapolation is different, but it's really hard to define all of this precisely.
Anyway, let's move on. So I think that it's very interesting. It's very useful that this paper is quite grounded in the 3 research questions, right? So I think that we should start by just reading them out loud and kind of clarifying what they mean. So the first research question that they explain, I just have it in here, is how do dense retrieval models extrapolate when compared to interaction-based deep neural ranking models and learned sparse retrieval methods? It's pretty self-explanatory. Would you add anything to that? Like, why is that interesting?
Just maybe some background that these dense retrieval models perform worse across domains. So I think this is why you might be motivated to look at extrapolation, right? So this is in between interpolation and totally changing domains, right?
Okay.
It's same document collection, probably same flavor of queries, and that they're natural language, kind of written in a similar way, you could say. But maybe the topics are different. And so I guess they have the idea of maybe we can start to see some difference between these dense retrieval methods and the others if we look at extrapolation rather than going all the way to switching the data set completely.
Okay.
Which I think is also interesting because dense methods have to do some kind of like lossy compression, to take a document and make a dense vector. So you could make an argument in your head that maybe it's really hard to do this when you totally change data sets because the documents look so different. Maybe whatever is learned for lossy compressing it, so to speak, breaks. So this is kind of interesting in that way, and that all of the documents remain the same.
No, that makes sense, and I think it relates. I think we can talk a little bit at the end about like what intuitive kind of thoughts you have about this, or like how you make sense of the results in an intuitive form and more intuitive perspective. But it also makes a lot of sense what you said about this research question is kind of doesn't come out of the blue, and it's more of when you look at the results from the past couple of years. In these BEIR benchmarks or like domain transfer benchmarks, it does seem like the dense retrieval break down more. So it's kind of a good hypothesis or something that makes sense. All right. Secondly, we have the second research question. How do different training strategies of dense retrieval models affect extrapolation performance?
Yeah, so I think we've talked about these a bit in past episodes. Well, for example, we looked at a pre-training strategy in the Spider paper.
Yeah.
So this pre-training can help. There we saw it starting to outperform BM25, I believe. But other things that have helped a lot that I don't think we've talked about in as much detail are like hard negative mining, for example, where you find really difficult negative examples, things that would not be so obvious to a human. So this tends to help a lot with training. And then the other thing is some distillation from a cross encoder. So the cross encoders are more robust. They tend to perform a bit better. So some distillation, looking at the cross encoders score and trying to distill that with a dense retrieval. more specifically like the difference in scores between a query in positive document and query in negative document distilled between the two.
No, that's super interesting because indeed, like my takeaway, and it's something I've mentioned before, but maybe not gone in depth, is that to make dense retrieval work, you need a lot of these tricks, right? It's not like plug and play. It's more like you need to set up the kind of the intuitive contrastive learning objective or something like that, and then add in and then you add hard negatives, or you do like distillation, you do all these things. And in the current benchmarking, it seems like that helps a lot, and it's a very salient question to ask: how does this translate once you have way more different training and test settings, like you're extrapolating instead of interpolating?
Yeah, definitely. And the story is a bit different here than what I had already or would have understood from other literature on this topic, because they split between interpolation and extrapolation. But I guess we'll look at that later. But like it doesn't totally mirror, what works well here versus other places.
No, exactly. Yeah. Okay, and finally, the third research question is about this relationship that we've already hinted at between interpolation, extrapolation, and domain transfer. Like their wording is: how does the interpolation extrapolation performance reflect domain transfer ability? Which is also pretty self-explanatory. Like how these things correlate.
Yeah, and I think it's pretty intuitive. They should be correlated in some way.
Exactly. All right, I think that we can. We can go into their analysis on defining train test label overlap, which is, I think, kind of important to understand what they do in this work, and then jump into the results, right? So they talk in section 4. They're called train test label overlap, which is a bit like Andrew has been saying, how much the training queries and the test queries have similarities, and there's different ways in which you can have similarities. Which is what they explain here. So maybe you can guide us a little bit through these concepts.
So they look at two types of similarities here. The first is entity overlap, which is basically whether the entities in two queries are totally the same, somewhat the same, or totally different. So if you have Bill and Melinda Gates in one query and only Bill Gates in another, well, this is partial overlap. Maybe it's worth pointing out that the surface forms of these entities don't matter. So if you said William Gates in one and Bill Gates in another, they still count this as overlap because they're using human annotators. So it's the actual entity. It's to the degree the annotator understands it, I guess, at least.
Okay. How much sense do you think that makes from the perspective of like the model? Because like the encoding of these tokens is not the same, actually, right?
Yeah, no, that's a good question. I don't have any data to back this up, but I would guess that there are really common surface forms that generally appear. So it probably doesn't come up often that you see a query that says, William Gates III rather than Bill Gates, or whatever his full name is. But that's just my intuition from where MS Marco comes from.
Okay.
Other ones, like you can think of USA versus like United States, for example. The models, both of these are probably common enough that the model can handle them similarly.
Ideally. Okay.
Yeah, so there's this entity overlap. And then there is intent similarity, which I would have liked to see a bit more explanation of. All we really know is that the queries are judged for whether their intents are similar, but there's not a lot of explanation about what kind of query intent. So for example, at a really high level, you could say a query intent is like navigational, you're looking for something, information on something, transactional, you're trying to buy a product or something. So like clearly they're annotating it at a more precise level than this, because I think essentially all these queries would be informational. But I don't know, where in this possible, very possible
like the
hierarchy.
Kind of abstraction layer of level of intent.
It would be nice to see like annotator instructions for this, for example. Maybe they'll release them later. But these are the two ways they look at similarity between queries. And then they have this method for finding possibly similar queries, which they're going to leverage later in the future experiments also. Basically, they take a query from the test set, and then they retrieve other queries using either BM25, so exact match based, or an embedding model. So this is, I believe it's ADOR. So it's one of these trained with hard negatives mining iteratively.
I mean, to give you more context, my understanding here is the question you're trying to answer, that annotator is trying to answer, is like for each one of the queries in the test set, is there any query in the training set that is like that way? Obviously, you're not going to go through like the millions of queries manually, so you just generate a set of candidates and hope that, you know, that they're going to have that you're going to have perfect recall, I guess, on that, on like potentially similar queries.
Yeah, exactly. I think they take the 10 most similar from BM25 and the 10 most similar from their dense method. Yeah, and then they'll reuse these later when they look at interpolation versus extrapolation. So these similar queries will become a proxy for interpolation later. But for now, they do human judgments on these. So for every test query, human judge 20 in terms of entity or intent similarity.
All right, and to give a sense of how much overlap there is between test and training set in existing TREC queries, can we just summarize table 1 and 2?
Yep. So table 1 is about entity overlap. So if we look at full overlap, meaning the entities are exactly the same, it's something like 63% in 2019 TREC, 54% in 2020, 45% within MS Marco's dev set itself. Partial overlap is, say, 30% for 2019. I think looking at one of these is enough. So basically, if we think about 2019, only 7% of queries have no entity overlap at all. 63% exactly the same, and 30% have partial. So it's quite a bit of overlap.
So you would say, like, intuitively, there's testing on TREC is pretty much testing on interpolation, according to how they it's like 90.
Yeah, if entity overlap indicates interpolation, yes. I think it's really hard to be precise because you could have different questions about the same entity.
No, you lose so much nuance once you formalize things into these categories. But still, it's useful to get a sense of how these things look.
Exactly. So for some proxy, there's a lot of shared entities between the training and test. And then we see something similar with the intent similarity, although again, it's hard for me to interpret these because I'm not entirely sure what is being annotated here. But looking at 2019 again, 51% are duplicate, 28% are similar. So only 21% are not similar at all. Similar, so duplicate means exactly the same intent. Maybe they mean something like this natural language versus keyword thing. I don't know if
like Bill Gates' net worth, or like what is the net worth of Bill
Gates? Or wedding dress alterations or cost of altering wedding dress, I think is some example they have in the table. So even the duplicate part is really high, right? Like 51%.
I guess, I mean, at the end of the day, like we intuitively understand what they want to capture with these sort of definitions of overlap. I think I agree with you that it's probably loses a lot of the nuance, or you lose a lot of that intuitive understanding of what makes two queries the same. But still, it's a good first step. Shall we move on to the resampling evaluation methods? Or do you have anything else we should say before that?
No, I think we can move to that. So I guess we should explain how this resampling is working.
Exactly.
They have two strategies, basically. So their goal here is to take some data set and to separate it into interpolation and extrapolation parts. So to do this, they build on that query similarity that we just discussed, where they find the most similar queries with BM25 or ADOR. So they have two strategies, like I said, for doing this. One is basically aimed at a small test set, and the other is aimed at a large test set. Basically, if your test set is small enough, like these TREC deep learning, these are around 50 queries, a bit less, you can just exclude everything similar to a test query from your training set, right? So they have those 50-ish deep learning queries. You find the top n for each. I think in here is 10 or 20, and you throw those queries away from your training. So it's fairly straightforward.
Yeah.
The other is based on the situation where you have too many test queries to do that. So, for example, MS Marco dev is 6,800, so you'd be throwing away
use pretty much all the training.
Yeah, exactly. So that's not going to fly.
Yeah.
So they instead try to cluster the queries.
Yeah.
So they come up with different clusters, basically analogous to folds, right? So to folds. So they have one cluster. Within that cluster, there's some train queries and there's some test queries. And so say you have 5 clusters. Well, you'll train on 4 of those, and then you'll report extrapolation results on the 5th. That 5th cluster has some training data and it has some test data, but you're leaving the training data out because it's similar to the test data in it.
Okay.
So it's kind of like constructing these.
It's a bit like doing like splitting a data set into parts and doing cross-validation, but you, instead of doing it randomly, you cluster them by top or by similarity, query similarity.
Yeah, exactly. It's just like some sort of 5-fold cross-validation approach. Yeah.
I think that's pretty straightforward, right?
Yeah.
Then we can just jump into the results.
Yeah, so they vary a few things as they report results. So they vary the training data size, either 14,000, 45,000, or 200,000. 200,000 is like a normal or full amount of training data, I guess.
Okay.
So they also look at smaller amounts on MS Marco. As you'd expect, more training data is better across methods. So I think we can look at the largest training data size where they're using all 200,000.
Okay. I think it's useful though, before we jump into the numbers. So we're talking normally in the abstract of like dense retrieval versus interaction based or cross encoder. I don't know what's the best term for that, but like interaction based or dense retrieval methods. So which actual implementations do they use, or like what actual models and why are you using those?
So they use a cross encoder, which is an interaction-based method, which is also a re-ranker because it's too expensive to rank everything in the data set. You find some candidates with BM25, re-rank them. So they're using this with BERT. All of these models, I believe, are based on BERT base, they say. Although the original splade is on... they're on a BERT variant. So this is using the CLS token to classify a query document pair. This performs the best. They have colbert, which is, you could say it's dense at the term level. It's not entirely clear, I guess, how to categorize it, but this is storing a representation of each term rather than a representation of the entire document. So the storage space scales with the document size.
Yeah.
This tends to be very robust compared to dense retrieval methods as you move across domains and that sort of thing.
Yeah, I mean, colbert... Actually, I think we're probably going to cover in the future episode. Maybe we're getting
this would be a good paper.
But colbert is one of the most famous right now, kind of neural IR methods, right? They're like more robust or kind of like gold standard.
You could say it's maybe the go-to method. So, I mean, compared to a cross encoder, it's not quite as effective often, but it's more efficient. It's more effective than dense retrieval approaches, but less efficient. It's a pretty good middle ground, I think, right now. And there's also splade, which is a learned sparse retrieval, meaning basically they learn new term weights to put an inverted index. So they're essentially replacing term frequency with like a measure of term salience or term importance to a document.
Which is learned.
Yeah, which is exactly, these weights are learned from training. And so what this gives you is a vector of vocab size over the query and over the document, where most, I guess, elements in that vector are 0. And then, of course, there's a dense retrieval model, which is the one they're training. This is BERT base. I believe here they're not training it with hard negatives or distillation or anything like that, just a standard dense retrieval.
Like in-batch negatives or...
That's a good question, actually. 1,024 random negatives per mini batch, they say, and across entropy loss. So it's only in batch, and they say they don't include the BM25 negatives.
Okay, yeah, so then it's just... Yeah, I mean, like we said before, it's kind of a shame that dense retrieval seems to be so sensitive to all of these kind of choices. As in, like, for instance, when you use in-batch negatives, increasing the batch size seems to be extremely relevant, right, for performance. So, like, some of these things are hard to investigate because of how much variation there is.
Yeah,
how
there's
you train your
a lot
Dense
of
Retrieval.
tricks required.
Yeah.
Yeah.
Anyway, but I think that covers the basics of the models that they're used here.
Yeah.
All right. So table 6, interpolation and extrapolation results.
Yep. So basically what we see is models get worse at extrapolation as you move closer to dense retrieval, I guess is how I would characterize it. So they split the queries like we described. They report interpolation and extrapolation. So for example, if we look at the cross encoder, there's almost no difference between the interpolation and extrapolation numbers, like 709 versus 705. And these are even different queries. So I wouldn't even expect there to be no difference at all. They're just different queries. They have different difficulties and properties. So they're really close here. This becomes a bit bigger when you move to Colbert, but not much bigger. So, for example, they say there's a 1% difference with the re-ranker, a 2% difference with Colbert. So not much different. This correlates with the observations that Colbert is good at moving between domains. With splade, the difference gets a bit bigger. It jumps to 5%. So this is somewhere in the middle. And then dense retrieval goes to 11%. So there's a much larger difference between interpolation and extrapolation performance with the dense retrieval method than with any of the others. So even comparing it to splade, the difference is from 5% to 11%. Comparing to re-ranker, the difference is between 1% for the re-ranker and 11% for dense retrieval. So fairly large in comparison.
And these findings pretty much translate across data, across sizes.
So they also look at the smaller sizes. These trends remain the same. Splade seems to have a bit more trouble with the smaller sizes, but the trend of re-ranker and Colbert being much better than the dense retrieval holds across all of them.
I guess something that is also surprising is the bit of a difference between the recall at 100 and NDCG at 10 metrics. What would you make of that in the sense that, for instance, between Colbert and splade, it seems to me like the trend is very clear when you look at NDCG, but when you look at recall at 100, they have some...
Yeah, that's a good point. So the ones I was naming were NDCG. So what stays consistent with recall at 100 is that the cross encoder is the best, and cross encoder has a little difference between interpolation and extrapolation. For recall, it's always less than 1% here.
Yeah.
But yeah, like you said, the other methods do become more close. So maybe looking at 200,000 data, 3% difference for Colbert, 5 for splade, 9 for dense retrieval. So you see some trends, but they're closer together.
Yeah.
Looking at the smallest amount of data, there's actually all are plus or minus 7%. So there's little difference there. But this is a very small amount of data.
Yeah, I know. I was just thinking because, I mean, of course, NDCG and recall at 10 have 100 have such a different sort of bias in kind of what is good, as in, right, in NDCG getting the top first right is kind of counts a lot, but for recall at 100 it's not really that important. But anyway, I do think that the gist of what like the takeaway from these results is pretty clear, like you have said. That said, in the what do they show in the table 7?
So table 6 was on the TREC deep learning. Table 7 is the same thing, but on MS Marco dev set. And here they switch sampling methods because the dev set is so large. So they switch to this clustering, like cross-fold validation type of approach. So we see similar trends here. There's a bigger difference between interpolation and extrapolation for the ranker. So this is now 6% rather than 1%. But as far as trends, they more or less hold. So Colbert is the next best. Dense retrieval is the worst or quite close to splade in terms of the biggest difference between interpolation and extrapolation.
Yeah.
So I guess this supports the previous results on another data set and with their other sampling strategy.
And like they point out, this pretty much supports or answers their first research question, which was how do dense retrieval models extrapolate compared to interaction neural ranking models and learn sparse retrieval models. And the answer to the question is they do worse, it seems. In terms of how confident you are in that finding, what would you say? As in, we've said, okay, dense retrieval as kind of requires a lot of, babysitting or like kind of nice, doing it very nicely. How confident you are that these results are kind of really answering this question properly and are not an artifact of how the optimization is done?
Yeah.
So to speak.
Combining them with other results, so like other results on the BEIR leaderboard and things like this, looking at generalization to other domains, which is taking extrapolation further, I would be quite confident in these because they're really consistent with what we see there, where cross encoders are just much better at that cross-domain setting than, for example, the single vector dense retrieval. But if I were to look at only these in isolation, I would maybe wonder a bit about whether these other tricks could matter much, right? Mm-hmm. So do hard negatives somehow improve extrapolation? Does distillation from a cross encoder somehow address this? Mm-hmm. Maybe the situation could change a lot with those. But because of the other results on these BEIR data sets, with tricks like this used, I know that doesn't solve the problem. So putting all this together, I would say I'm pretty confident.
All right. No, I think that's a very good, nicely packaged takeaway.
Yeah, and actually they look at this to a degree in one of the next tables, right?
Yeah,
so they
exactly,
look at
exactly. So I think that's a very good transition to the next section of the results, which is precisely comparing dense retrieval training methods, right? Like we've said, dense retrieval is sensitive to how you train them and like all of this. So that's pretty much what they look at table 8. So what do we see here?
Yeah, so they have 3 things they try here. One is replacing random negatives with hard negatives. Another is replacing the normal training objective with distillation from a cross encoder. Mm-hmm. So this is, I think, with margin MSE, trying to mimic the cross encoder's score difference between positive and negative document, I believe. And then replacing the checkpoint. So rather than standard pre-trained BERT, doing some sort of additional IR-specific pre-training and then starting from there, rather than from the original BERT checkpoint. So they try each of these 3 in isolation. If we were to think about prior work that exists, we would expect to see the biggest improvement, I think, from the hard negative mining. I think the second biggest from distillation. And then maybe pre-training comes in third. That's at least my intuition. Mm-hmm. You can't argue with this. But what we see here is the opposite. So the only thing that really makes a difference is this pre-training. So talking again about percentage difference between interpolation and extrapolation, we started at 14% difference, looking at TREC deep learning. If we do the hard negative approach or the distillation approach, this 14% only comes down to 12 or 13. Mm-hmm. So it's very little impact. Whereas if you instead change the pre-training task to co-condensers pre-training on MS Marco, so also on this target document collection, that drops from 14 to 6%. So this is cut in half, whereas the others had little impact.
That's really fascinating. Yeah.
Yeah. There's caveats, right? So maybe if you combine all of these, they could help. I don't know.
No, but I mean, from an intuitive perspective, hard negatives, does it make sense that hard negatives don't help or help very little with extrapolation, but do help so much with interpolation?
It's hard to say. Hard negatives, if you want to make a hand-wavy argument, I guess you could think about maybe they're focused on interpolation because you could be replacing just 1 or 2 terms. So this I would view as interpolating between only a small replacement and showing that this became negative, right? So you swap that entity out and now it's negative.
Yeah.
But it's really hand wave.
Totally. I mean, I guess what I was thinking about is a little bit in those sense, like when you think of hard negatives, is you're kind of like giving a model examples of things that are very close and which one is kind of good and which one is bad. And I would kind of assume that kind of is a learning signal for this more fine-grained interpolation kind of type of differences. But it's also not very...
Well, so actually one hard negative approach by Sebastian Hofstetter works by clustering queries, and then hard negatives come from the same cluster. So I think here, if you think about them as clustering, you can kind of see the relationship to interpolation, because in the cluster, maybe you swap out 1 or 2 terms or something, and most of it's the same.
Mm-hmm. No, totally.
But there's, of course, a lot of ways to mine hard negatives.
Absolutely. But anyway, I guess that the main important takeaway is what you just said, that these techniques, these advanced techniques for dense retrieval don't help. Or like pretty much results are consistent even when you start using all of those things.
Yeah. It's unlike prior work, these don't seem to matter so much when you look at interpolation versus extrapolation. It's distillation. So this is distilling from a cross encoder. We know a cross encoder is better at extrapolation. Yeah. So maybe distilling from that should help. But not what we see here.
Okay. That said, is there anything else? So this pretty much answers their research question number 2, right? Which, just to recall, this was how do different training strategies for dense retrieval models affect the extrapolation performance? So the answer to this question is the only one that substantially or like most meaningfully affects is the pre-training objective and not so much the fine-tuning.
Right.
However, you said that you had some kind of doubts about, well, not doubts, but kind of, you would like a bit of further investigation on this because this was done on a training set that is not too large or like...
Yeah, it was done on their middle set training size. It would be nice to see it on the larger training set so the numbers are closer to the maximum reported, but I wouldn't be that surprised if trends still hold somewhat. But I'm just speculating.
But is there any like any reason why you would have a suspicion it wouldn't hold, as in like any suspicion that when you go from like low data to high data regime, these augmentations or these techniques change a lot? How like their effect changes a lot?
I mean, maybe, for example, the importance of hard negatives starts coming into play when you have a lot of training samples. I don't know if 45,000 counts as a lot here, but 200,000 is obviously more, right? Maybe, finding challenging negatives has a bigger impact as you have more training data. But I don't really know.
Okay. No, but that, I mean, doesn't seem to invalidate the kind of general gist of...
No, I mean, it's quite interesting that it's different than the story we would tell from prior work. Like, something is going on, it seems.
All right. And that brings us, I think, to the last bit of their results section, which looks at the research question number 3, which is about how interpolation and extrapolation relates to domain transfer. Like, are those things very much related or not? So how do they look at that?
Yeah, so what they do is they take these 8 models that they've been using in prior experiments, along with the 3 sizes of training sets, and then they kind of rank how they compare on BEIR, so on these other data sets, and how they perform for interpolation and extrapolation.
Yeah, so maybe we can just have a quick mention of what BEIR is as a benchmark.
Yeah, we may not have talked about this actually. Yeah, so BEIR is a collection of benchmarks. They're all a bit different. You have things like biomedical retrieval. You have things that are farther from normal ad hoc retrieval, like returning arguments or counter arguments. Counter arguments particularly is a bit weird because you have an argument as a query and you should find counter arguments to that. Okay. It's really different than a normal retrieval task. Yeah. But it's a bunch of data sets like this, very roughly around, I think, 12, 15. And the idea is to not train on them. So to train on something like MS Marco and evaluate how well you perform on these data sets. Most, if not all, don't have sufficient data for really training a dense retrieval model anyway.
So the kind of goal of this benchmark was to focus on the generalization of retrieval models and to evaluate that.
Yeah, exactly. So the goal of this is to have a conversation about how well these models generalize to new domains and new query types. The point being that, what does well in MS Marco doesn't necessarily do well here. So this is why they have these data sets, and then they use this to compare how well methods do on these data sets, which is out of domain, with how well they do on interpolation versus extrapolation. Right. So if you can pick a model that interpolates well, or you can pick a model that extrapolates well, which one would you pick to report results on one of these is one way to put it. And I think the intuitive conclusion which they support is you would pick extrapolation, because moving to another domain you could think of as a more extreme form of extrapolation, right?
Yeah.
It's just extrapolating more.
Yeah.
And they quantify this by looking at correlation. So for those 8 model settings, 3 training sizes, they basically rank them, and they look at the ranking on a BEIR data set versus interpolation performance versus extrapolation. And the extrapolation performance is much better correlated with how they perform on almost all of these data sets.
Yeah, so we're basically looking at figure 2, where we have this sort of scatter plot, right?
Yeah.
For the interpolation versus extrapolation results, and you can see that the extrapolation results sort of more or less align in a nicer, well, closer to a kind of line or a kind of monotonically increasing type of function. Right?
Yeah, there's more correlation between the two, extrapolation performance and data set.
This seems pretty intuitive. Like you've said, it seems like domain transfer is pretty much on the same spectrum of extrapolation, just kind of more extreme case of that. Do you think this kind of, in a way, there's as in, like, could these techniques for measuring extrapolation replace data benchmarks or data benchmarks like BEIR, or they're kind of, what their measures is still different enough that
I think they measure something different, and they're really complementary. They have a lot of different trade-offs. So if you look at like extrapolation, you can't change the documents, for example, right? You're only changing queries at the end of the day, which is really nice, in that you've eliminated this source of difference. But you know, there would be reasons also to change the documents, right? If you actually do want to know in a cross-domain setting how things will work. So I see it as complementary. It's kind of, to me, it's identifying a point on the spectrum that we may have missed, where we think about in data set evaluation, and then we think about transfer. But I think it's a really nice point to think about what's in the data set and split it into the interpolation and extrapolation. When we have a data set this large. So I see it as something more complementary, but maybe something that's a bit easier to do. They argue this somewhat in the paper, because you're just slicing and dicing the queries and judgments you already have. You don't need to create something new. So, you know, you can think about a lot of different types of extrapolation, and you could evaluate them in different ways. So like they have the entity overlap here.
No, I mean, I guess it's something that's also interesting about this method that they propose, is that I can see how it could be somewhat extended to some kind of automatic setup where you find, look at similar queries from the test set, and then you do this slicing and dicing, but in some automated clustering way where you can kind of dial the extrapolation, interpolation kind of dials a little bit, and see how this thing kind of evolves to like more extreme cases versus more kind of mild cases of interpolation.
And even different types. Like, is the relation what you extrapolate, or is the entity, or, what changes between...
Yeah, exactly.
Yeah.
Okay, I think that covers pretty much the results of this paper. I think it's pretty simple, and the takeaways are pretty neat. So the answer to the third research question is... it's pretty much the research question was, how does interpolation and extrapolation performance reflect domain transferability? And the answer is, it kind of does.
And extrapolation is much more correlated with it.
Exactly. Extrapolation is more correlated with domain transferability. It's still not one-to-one completely, so there's still a lot of insights that are different that you might take from these two benchmarking options. But that's pretty much the gist of it. That said, in terms of a more broad stroke conclusions, what in this paper, I don't know, is there a big thing that changed, a big perspective that changed for you in this after reading this paper? What surprised you, or what are also like weaknesses or like things that could be done to kind of make this paper more useful than it is now?
So I think this identification of extrapolation performance is something we should study was a nice insight. I think that I would expect others to pick up on this and to look at it in different ways, especially because you can only do it approximately, right? This is based on query similarity, so even this part could be improved. There's
like you said, a lot of things are ill-defined or hard to formalize.
It's just a difficult topic. But the most surprising thing to me, I think, would be these dense retrieval results. So the fact that pre-training has such a different impact, I would be very curious, to look at these with larger data sizes to try to compare them. Like if we do the best possible thing, some good pre-training, some hard negative mining, I guess distillation also. Do we still see a big benefit from pre-training when we look at interpolation versus extrapolation? And do we see the same benefit if we just look at the data set without considering these separate dimensions? Is not clear to me. From what I've seen in pre-training work, it seems looking at these results that there is a big benefit for extrapolation that I just hadn't seen when looking at some of these original papers. It seemed to me that the improvement from the pre-training was smaller than what we see here.
That's a very good point. Because that seemed to be a very robust finding, that pre-training doesn't matter all that much. It's more about the hard negatives, the distillation, the batch sizes or stuff like that.
I think it seems like it's possible to do pre-training in a way that will improve, but you would always pick hard negative mining or distillation first from the results I've seen. And the story is totally different here. You should start with pre-training according to this. So that's very interesting, and I think that's the most surprising result. Other than that, it's a nice confirmation of how this all relates to domain transfer, I think, and it's a nice way to think about things. It gives us a way to separate, like I was saying, like the document collection from other factors, right? So just freeze the document collection, but try to split the queries up and look at them in different ways in relation to how similar they were to the training data.
I think that this also goes in this trend of something we had talked about, which is to stop only looking at the aggregated results from benchmarks and start to trying to opening the black box that benchmarking is and like playing with that and see what comes out, right? Because often two models might perform very different qualitatively, but at the aggregation level have the same NDCG at 10. Yeah. And that's very interesting from a research perspective. It's almost necessary from a research perspective because we're getting so good at some of these benchmarks that it's hard to know what to do unless you find another way to look at the benchmark, or I guess replace the benchmark, but that's not so easy. It's nice to have, rather than making the main average MS Marco number go up, to be able to look at extrapolation and try to understand what can improve that specifically. There's probably more room to improve there than just looking at the average. So in terms of, you've mentioned that a few minutes ago, in terms of the intuitiveness of this, you've said you might not, I think your wording was this seems intuitive in hindsight, but you might not have predicted these results if you were asked the question. So how would you make sense? How do you make sense from this intuitive perspective, the fact that the dense retrieval performs much worse than sparse methods at extrapolation?
Right. So if we compare it to splade, which actually in this paper they call it dense in some way, it's very confusing because the vectors are a vocabulary size. But if you think about a vector of vocabulary size, there's nothing really lost here, right? You know exactly what term appears. You can get the weighting wrong for a term, but you know what's there.
Yeah.
With these smaller dense vectors, so there's 768 dimensions here and dense, whereas the vocabulary size vectors are sparse. Most of them are zeros. Here, they're essentially all non-zero. There has to be some sort of, you could think of it as lossy compression. There has to be some translation of what terms occur to this dense vector. You can say it has some semantic meaning, I guess, but at the end of the day, you need some kind of translation. Maybe swim and swimming are translated similarly into that vector, right? Similar concepts, but you need some translation. And this translation step should appear, I think, in extrapolation more than it does interpolation, because you now are taking terms that you have seen less during training and trying to put them in that semantic space, so the 768 dim encoding. And this should occur even more, I think, when you're moving to a cross-domain, because you're potentially changing a lot more about what terminology can even appear and so on. So I hadn't thought of dense retrieval as being related to extrapolation, to have what queries you've seen before. But in hindsight, to me, it seems like a clear relation, because if you're doing interpolation, if you're handling a query that's similar to what you've seen before, you probably can successfully encode that into the 768 dimension vector. You can put it in the right place in your semantic space. It's easier too, because you've seen a lot of similar things.
Okay.
And this step is what's difficult for single vector dense retrieval, which have to do this encoding, and it doesn't seem as difficult for like Colbert or the re-ranker. And we see this also with extrapolation, right? So it's not just that moving domains is what's difficult. It's probably tied to the difficulty of this translation task, or compression, you can call it.
Yeah.
And it highlights like a middle ground where we can see this difficulty where we couldn't earlier see it on MS Marco, right? Before, maybe Colbert is a bit better on MS Marco, but dense retrieval methods seem to work well. Colbert seems to work well. You move to BEIR, dense retrieval totally fails. Colbert still's kind of working reasonably.
And I think that is a very interesting finding if these can replicate across even bigger dimensionalities and even bigger training data sets, and like the hard negatives, the large batch sizes, as in, if this extrapolation interpolation difference remains as you scale things up, it might be a kind of a big barrier to cross for dense retrieval in this sense, which is relevant.
Yeah.
And there's not that much more. Like how another thing that you could reflect a little bit on is how much do you think these will have an impact on shifting the benchmarking or evaluation culture, or like do you see people applying this trick or method in future works a lot, or is it just something that?
Yeah, I hope so. I don't think it will become the most common way to look at things. Like for MS Marco, probably reporting the average will still be the most common, but I hope to see it used more in other papers. And I hope that papers investigating pre-training look at it specifically, because it seems, we see improvements in this paper, but just thinking about this mapping to the semantic space, it seems really related, right? If you're pre-training on those documents, you probably can have a better mapping, which you see in the results here, that it does improve.
And absolutely. Like you said at the beginning, benchmark is so fundamental to like the progress and in research, and like finding a new way to measure something, uncovers phenomena that you were blind to before. Like it might be this, and this is kind of exciting because it might open new avenues of insights.
Exactly. It's a great way to put it. I think it makes room to improve in different ways you might not have known were ways that you could look at before.
So is there anything else you'd like to highlight before we close it off?
No, I think that's about it. It was a nice paper. I would like to see, I would really like to see more mention of exactly what intent means here. But other than that, maybe they ran out of space.
No, but it's a very valid, I think, critique, because I always said it does make some intuitive sense, but then at a more concrete level, this annotation process is a little bit more obscure. Yeah,
I almost think they're talking about whether the information needs are the same, but there's no way to know for sure. Yeah.
All right, so that was it. I also really liked and enjoyed this paper. Really recommend checking it out. Thanks for joining us, and I will see you in the next episode.
Thanks.